Damn, did I kill it? It's going so well and I pressed the wrong button. Watching to see if my stream comes back. Damn. Hopefully it's going to come back now. Yep, looks like it's come back. Right, okay. Are we back? Are we back? Okay, I think I'm back. I think I am. Let's just copy that link. Great. Okay, so thanks all those out there in WhatsApp land letting me know that I buggered up and I had to relaunch that. You wouldn't believe it, I was trying to resize the window and I clicked by accident finish live stream. Mistakes for beginners. All right, but I'm going to edit this later on, so I'll just carry on where I left off, and that way you won't have to listen to me do another whole intro. So let me bring that up. There we go. Okay, so where were we? We're back on the scope of 5033 and what are the major changes to it from the previous edition. So requirements for labelling of cables and cable protection, labelling of conduits and type of conduits, connector requirements, new signs and other commissioning requirements. So let's just jump into it. DC conditioning units. Wow. Now, these are, yes, some people love them, hate them. They're more little boxes on the roof, but they provide definite advantages when it comes to things like safety, performance, monitoring. But they had a problem in the previous version of 5033, the 2012 edition. They weren't really recognised, and that meant that we were seeing these perfectly good systems being disadvantaged by the fact that the previous standard required you to put a DC isolator on every piece of power conditioning equipment, which would include DCUs or optimizers. And that just wouldn't be practical. Imagine putting a DC isolator under every panel on every optimizer. So we clarified that in the 2014 edition and said, no, not required. They're a special purpose of equipment. We still need isolation on the array, but not on every single DCU. So that was a big plus. We did limit the definition to 350 watts. And back in 2014, that seemed like plenty, but what do you know, panels have got bigger and bigger and bigger. So back then, panels were around the 150 to 180 watt mark. Now they're 300 plus, 400 plus. Jesus, there's 500 watt panels out there now. So that's one of the things that's being revised is the definition of a DCU and what the maximum power of it is without having to have individual isolation on each one. So here's the summary of those changes to DCU requirements in the 2014 edition. It includes 4 major things: that the cable length to the DCU can't be more than 1.5 meters. You can't extend the fly leads of the panels, except you can put adapters. Now the reason for that is you must have like-for-like connectors on all your panels and anything they connect to, such as DCUs. And there isn't a standard for DC connectors. There are lots of different brands. Many of them kind of work together. You sort of plug them in and you think they're the same thing, but they're not manufactured to be pushed together. And therefore, we require that all plugs and sockets are the same brand, same type, both sides of the connection. But so you are allowed to use adapter cables to overcome that, where your DCU, your optimizer, has brand X plugs and sockets on it, and your inverter has brand Y, and you can get a short adapter. As I mentioned, no more than 350 watts at standard test conditions, PV power, and the panels must be extra low voltage. You can have multiple DCUs in one package. These are not very common, but there's a few out there. But you do need to have an input for each DCU, and maximum 350 watts again. The PCE DC isolator requirements. If the DC conditioning system unit has a fail-safe so that the open circuit voltage of the array is that of the inverter's maximum input. Now, that's kind of complicated, the way I've said it. Basically, you might think putting 20 panels in a string is going to get well over 600 volts, which is the upper limit for residential systems in Australia and New Zealand currently. But when you put DCUs on every panel, they control the voltage. And many of them will start at 1 volt until the inverter tells them to turn on and tells them what voltage the string should be. So it's actually the inverter that controls the string voltage. And therefore, if the inverter's got a maximum input voltage of, say, 600 volts, it doesn't actually matter that you've got 20 panels out there in a string, which notionally, if you just took the VOC of each panel, would be greater than 600 volts, but the DCUs control it. So that's one of the reasons that you can get away with this by using DCUs. Now, I just saw a text message that we went offline. I'm just going to send a link to that person so they know that we're back on. Okay, that's good. Yep, so getting a few messages coming in about the dropout, so very sorry about that, people. And I'm just going to share the link with those people who just texted me. There we go. Good. And there's a picture of the DCUs and explaining how they work. So each one interfaces between the PV array and the string of panels that are connected together in series, and therefore they are controlling the string voltage collectively. In fact, there are different systems for this. Sometimes the inverter, in this case, we use the generic term PCE, power conditioning equipment, because it may be other than an inverter, but generally it is. It's telling each of those DCUs what their current and voltage should be to get the target string voltage that the inverter wants. So that's how they work. This is actually a picture of mine, well, it's actually from Google, but it's a picture of a system I put in back in 2009, I think. It was the first time I ever used DCUs, and these were, it's a solar edge system, and this is a 2-story house. I think there's 1, 2, 3, 4, 5, 6, 7 different orientations and inclinations on this roof. So the panels are scattered like playing cards across the building, but they're actually all in one string. So it's pretty amazing that you can do this. But the benefit is that the customer actually gets to have a reasonable sized system on a very difficult roof for solar. I must admit, I was kind of tried to talk the customer out of it, saying, look, your roof is really not suitable. And they put it to me, that's not my problem, that's your problem, Glenn. Come up with a way to put solar on my house. So we did. We used optimizers. So in the standard, it says that all modules in a string must face the same direction, plus or minus 5 degrees of inclination and azimuth, that's compass bearing, unless they have individual maximum power point tracking devices. And that's what a DCU is. It operates each panel independently of every other panel. So that's the solution to that problem. Microinverters. Now, generically, both optimizers, DCUs, and microinverters are known as module level power electronics, or MLPE. I won't use that acronym much, but I'll just talk about microinverters and optimizers. Microinverters are a similar function to a optimizer, but they convert from DC to AC. So you've actually got a AC network up onto your roof, and every panel, the highest DC voltage is one panel, because there's no strings of panels connected together in series or DC strings. The advantages of microinverters, therefore, is safety. You've only got an AC network on the roof, so that your normal overcurrent protection systems in the home will protect that circuit. You don't have the risk of arcing that you can get with DC at higher voltages. They give you the same benefit of optimization at a module level and monitoring. So both microinverters and DCUs or optimizers generally will give you a monitoring solution as well that allows you to see the performance of every panel. Same requirements as a optimizer, maximum length of cable 1.5 meters, no extension on cables. You can use DC adapters to adapt between different plugs and socket types. If you've got multiple optimizers in a single package, each needs its own MPPT, maximum power point tracker, and each input must be less than 350 watts DC at standard test conditions. The multiple input micros are pretty rare these days, but as long as they're ELV on the input and 350 watts per input, then they're fine as well. And I think if I go back a slide, there is actually a picture in the top left of your screen of a microinverter with multiple panels connected to it. But if you look carefully, there's actually only one input, and so it's using Y connectors. Now that would not be compliant. You can't use Y connectors, you actually have to have individual MPPTs for each panel. PV frame earthing, equal potential bonding, or equipotential bonding, I should say, is a special definition of earthing. It's not a protective earth, it's not a shield earth, it's kind of a hybrid of several things, and the purpose of it is mostly about detecting if there is a fault between the DC side of a PV array and earth, and therefore having a reference point to earth on the conductive parts of the module allow the inverter to see that fault, raise an alarm and turn off. So it's for sensing faults as opposed to providing a fault path for current. The minimum cable size, I'm a little bit in the way with my picture there, let's move it up, is 4 millimeters square. That's really about mechanical robustness. Even though there's virtually no current flowing through this, even in a fault condition, it's pretty light. It's there just so it doesn't get broken, really. But there is some circumstances where you would have to increase the size of that, such as if it's part of a lightning protection system. The lightning protection standard says minimum of 16 millimeters square. Or if the fault current could be greater than 4 millimeters square cable could carry. Okay, bring myself down again. So all LV PV arrays require bonding of the module frames and mounting system. Now, what I mean by low voltage PV arrays is systems over 120 volts DC need to have the conductive parts of the modules and frames and mounting systems bonded to earth. This is usually done using what is called bonding washers and an earth lug, but there are other means to do it. The purpose of this is to provide a common path to earth on all of the conductive parts. And the requirement also is that if you remove any one panel, you don't compromise the earthing system. So you can't just daisy chain panels together. You need to actually have effectively either an earth bar using the module mounting system or a continuous earth that each module connects to. And we've got a question here. Let's have a look at it. Okay, so thanks, Dave. Does the earthing cable need to be tinned? Now, there's a requirement in the standard that there is a definition for the PV array cable. The PV array cable has to meet a certain solar standard. It's often just referred to as solar DC cable, but that doesn't apply to the earth conductor. So no, you don't actually have to use a tinned earth conductor, but you do still need to mechanically protect that and protect it from UV. So it's quite common just to use 4 millimeter standard earth conductor wire in parallel with the DC cables in the same conduit. And that's a very convenient way of doing it. Thanks for that one, Dave. For microinverters, they actually have AC coming up to them. So as ASNZS3000 would require, they actually need to have an earth bond to the conductive parts of the module, of the microinverter. And since you've already got an earth coming up to the microinverter, it's practical to use that as your bonding terminal for your array as well. And you'll find that many of the manufacturers of microinverters, though there's not many left really these days, will provide you with that earthing terminal. Though there are some which aren't made of metal parts, and therefore they're double insulated, and so you'd still need to bring an earthing conductor up to the array in that case. Segregation. Now, segregation is one of those topics that's been covered in ASNZS 3000, but it was covered really considering DC as a telecommunication signal, not as DC as a power transmission system. And in ASNZS 3000, it refers to segregation on voltage level, that means LV or ELV, and telecommunication cables. However, a 600 volt DC cable is the same voltage level as a 230 volt AC cable, and just reading ASNZS 3000, you would think you don't need to segregate them because they're both the same voltage level, and neither is a telecommunication service. But we amended ASNZS 5033 to include DC cables as a special category. And so you are required to segregate AC and DC circuits within enclosures to IP4X, that's a 1mm probe, and 50mm of separation outside of enclosures. Otherwise, ASNZS 3000's segregation requirements apply. Okay, I just saw a news blast come through from New Zealand. The government announcement on lockdown. So let me know in the comments, New Zealand viewers, what the latest on the lockdown is. So segregation requirements there, I've covered those off, I think, in my spiel there. If a common mounting rail, then must be non-conductive. Now that means inside an enclosure. I'm talking about the DIN rail inside an enclosure. If you do have a DIN rail that spans two sides of an enclosure, the DC side and the AC side, it's either split or non-conductive. Where you've got in the same enclosure AC and DC circuits, they need to be differentiated by colour. So you can't have a positive red and an active red. And outside enclosures, 50 mils of separation. PV cables inside buildings. Yes, someone said. Thank you, Chris. Just pointing out, time to go surfing. So, Chris, I presume you're in New Zealand then. Yeah, that's right. So, lockdowns can sometimes give you a bit more free time, though not much socialising as part of it. So, cables inside buildings require mechanical protection, and we specified in the 2012 edition that the protection was HD conduit inside buildings. But what we didn't say very well was what was actually inside a building. And we defined it much better in the 2014 edition, where we said it's within ceilings, wall cavities, and under floors. So that's a better definition than just inside buildings. It doesn't apply to the earth conductors, so you don't actually have to put the earth conductor, the equal potential bonding conductor for the array, inside HD conduit, but you might as well. It's just one less bit of wire to kind of drag through the building. There is a little exemption on the HD conduit requirements too, which is you can have up to 300 mils of DC cabling not inside conduit at the terminals of the inverter, as long as they are adequately mechanically protected and the system is below 600 volts. And that's really looking at from an ASNZS 3000 perspective. Is it installed a location where it won't be, those cables won't be damaged by location? And that's really to accommodate the fact that many inverters use a plug and socket connection for the PV array, and it's not practicable to conduit right up to the inverter's plug and socket connections, so we allow that 300 mils. And also to remove the inverter, you need to be able to unplug them, and it would be difficult if it had conduit over it. It's not a requirement, by the way, HD conduit for non-domestic installations, where there is another means to minimise risk. And so I'm just going to move myself up a bit there. So minimising risk can be, once again, by location. Think about the clauses in ASNZS 3000 about protection of cables, and if you're putting them out of harm's way, out of reach, maybe in a commercial installation in cable tray close to the ceiling, it doesn't. The DC cables could go in there as well, as long as you got your 50 mils of separation between any other circuits of AC or telecommunication or data. They could go in that same cable tray and wouldn't have to be in HD conduit. So just pointing out that AS3000's mechanical protection applies to DC cables as well as AC cables. Restricted access. Yeah, so I like this sign. People don't read signs, do they? Maybe they do. I just thought this one really emphasised the fact that they mean do not touch. Yeah. So we introduced a more clear definition of restricted access in the 2014 edition, and we pointed out that for systems over 600 volts, restricted access has been required since 2012, but we didn't give a very good definition of restricted. So it can be restricted by a range of things, including, what do we got here? A barrier such as a fence, padlock gate or locked door, restricted by location such as a roof, with no ready means of access, i.e. not a permanently fixed ladder. Over 600 volts, all DC cables, including the protection and isolation devices, must be restricted, so access can only be by the use of a tool, and that includes the plug and sockets. So effectively that means once you go over 600 volts on the DC side, and that's VOC max, under the coldest conditions, you're going to have to encase in conduit or duct or cable tray all of the DC cables right up to the terminals of the inverter. Now that actually includes a DC isolator if you happen to have one. So if there's not an integrated DC isolator in the inverter, the DC isolator itself is actually restricted access. You might think, hang on, it's a switch. Well, it's not really an emergency switch. It's there for maintenance and service so that you can turn off the DC from the array if you're working on the inverter. So it's there for authorized workers, so hence it's restricted. We better defined adjacent. It said that you needed to have isolation adjacent to an inverter within 3 meters and fully visible from both locations. Now that would apply to the DC side of the inverter and also the AC side of the inverter. And the reason we put fully visible there is it can't be around a corner. The principle of having isolation at a piece of equipment is so that you can work on it and see that it's turned off. So that requirement to have fully visible would preclude things like the isolators around the corner, or it's through a door, such as an inverter outside the house and the main switchboard, or is a flush mount board inside the house in the hallway. That's not fully visible from both locations. We better define domestic installations. We specified domestic dwelling was using the National Construction Code of Australia. I'm not quite sure what the equivalent in New Zealand is, but a class 1, 2, 3 or 10 building, which is a single dwelling. I'll just move myself out the way. Units, boarding house or shed are all considered domestic, whereas the others are exempted from that domestic definition. We removed one little anomaly, which was requiring anodized array frames in marine environments. You just have to follow manufacturer's requirements. So if the modules or frame aren't suitable for being close to the sea, then you can't use them. The labelling requirements, we increased the labelling requirements on the conduit to be every 2 meters, and that would be visible. So once again, you might have been used to, certainly if you did your electrical apprenticeship, of hiding the labels by turning them towards the wall on your conduits. Now you actually need to display them. Now, companies like Marley in New Zealand actually print the DC warning labels onto their conduits, so you can just make sure that's visible. And in a roof space, if they're not easily visible, you might want to tag them as well. The fire and emergency sign, move myself out of the way again, is required to have 2 pieces of information: the short circuit current of the array and the maximum open circuit voltage. Now that isn't just look at the back of the panel. It says the panels are 45 volts and you multiply that by a number of panels, might be 10 of them, you go, oh, that's 450 volts. No, that would be wrong. In fact, if I see a nice round number written on that label, I guess they probably haven't calculated it, because you need to calculate for the coldest operating temperatures. And there's a table in 5033 to give you multipliers for different minimum temperatures, ranges, like 5-degree ranges. The short circuit current is that given on the back of the module. So if you've got 1 string, it's a short circuit current of 1 string. If you've got 2 strings in parallel, it's a short circuit current of 2 strings. It's basically to provide emergency services with information about the risk. Where DC conditioning units are used, we can use the maximum voltage of the inverter as the VOC, and the DC current is that of the inverter as well. So because the inverter controls DCUs, we can use the inverter's input ratings as the maximum voltage. And here's an example of a data sheet for an inverter with and if it was connected to DCUs, because this inverter can operate at up to 800 volts, even though its MPPT range is 350 to 600, we'd actually have to consider that this system is restricted access because the inverter is capable of operating the array above 600 volts. And there's an example of the warning sign, that's sometimes called the fire sign, for a AC solar array, i.e. microinverters. And the wording indicates that since it's an AC solar array, and you've got to say where it is, that you need to turn off the main switch for that inverter supply, and that it doesn't de-energize the PV system. Probably not a big deal, given that with microinverters, the maximum voltage on the DC side is just one panel. There's the new shutdown procedure sign. Keep it simple. Many kits will already come with this. We added that yellow section and the hazard sign to the bottom there. And it points out that the turning off the DC isolator at the PCE, at the inverter, doesn't de-energize the array or its cables. So there's still live cables in the roof, for instance, or up on the roof, but you've just isolated at the inverter or maximum power point tracker. So that's a little overview of 5033, but what I've got is a little additional piece on DC isolators and their voltage rating. So let's just jump over to this. Now, the reason I've added this on is a kind of a request from one of you out there, is to talk a bit about how to choose a DC isolator. Now, the thing that newcomers to this industry find surprising is that there isn't actually a standard voltage for switchgear. You might be used to, going to a wholesaler and buying a 6 kA circuit breaker for a domestic application, or a 10 kA for a commercial, but you just know that the voltages are what they are. They're the grid voltages, so you don't actually have to specify a voltage rating for your switchgear or your cable protection equipment. But with a DC array, you actually construct the voltage by putting panels together in series. So there isn't a standard voltage. Small systems might be hundreds of volts, and large systems might be way up, close to 1,000 volts or more. And therefore, the switchgear needs to be suitably rated. But it's not that simple either, because it depends on the topology of the inverter. Now, here's a data sheet from a DC isolator manufacturer. And remember, most of these manufacturers are global manufacturers, so that they're not necessarily making their data sheets for our particular standard. And therefore, they're just showing that, in this case, the 3-pole device has a 750 volt rating, but they're showing that all of the switching is on the positive side. So there's 3 poles in series on the positive side and a common negative. So we actually don't have a double-poled isolation on both the positive and the negative. And that's common for systems where the negative conductor might be grounded, for instance, though it's very uncommon these days for grid connect systems to ground the negative conductor because of the topology of inverters. The picture on the right there is showing a 4-pole device, and 4 poles can be wired in different combinations of series and parallel for different outcomes. So I'm going to run through the problem just with a picture here. Now, this picture, I'm going to quickly draw this on my drawing pad over here. So let me just cut across to my drawing pad. There we go. All right. So what we got here is, where's my little sketch gone? There it is. So I've drawn a very simple representation of a single string array, and this system is connected to a inverter like this. It's our inverter, and the inverter converts to AC. So there's our AC output. Okay, and so we've got a positive side to the inverter and a negative side to the inverter. Now, what used to happen, and I say used to because inverters have really changed over time, is that they used to have a transformer inside them that galvanically isolated the AC side from the DC side. And therefore, any faults on the DC side had no impact. So if I draw a fault on here to earth, that fault, there is no reference to earth on the positive or negative conductor in this diagram. And therefore, that fault actually does nothing. It doesn't actually create a fault current. It's just referencing one of the poles of the array to earth. It may significantly impact on the inverter's performance, or it may not. The system's floating. It's unlikely to impact unless there's some earth fault detection system. But these days, we use inverters that have what's called they're non-isolating, and therefore, and there's the symbol for an inverter, and before you shoot me, you don't have to put the AC and the DC on the side that the connections go. It's just a convention of a drawing for a symbol. So it converts DC to AC, but inside there is no galvanic isolation. So you could think of the connections like this. When the inverter's operating, the DC is directly connected to the AC side. It actually switches back and forth, 100 times a second or so, and that's how it generates an AC waveform. But when it's operating, there is no galvanic isolation between the AC side and the DC side. So here's our earthing point here, and we've accidentally earthed over here. So while that system's operating, we're going to get a fault current that goes like this. So it goes right through the DC side, right through the inverter, usually destroying it, back through the transformer, back through the neutral, through the earth conductor, and that's a bit scary when you think there might be DC flowing through your switchboard, through your earth conductor, without you knowing about it. So removing the main earth could be a little bit hazardous. So the reason I've drawn this picture is to show that one of the poles of the DC isolator has no fault current flowing through it. So we actually have to consider, with transformerless inverters, the voltage rating on each switched leg of the isolator. So if I've got 550 volts here, open circuit maximum, I could have across here, as it switches, 550 volts on just one switched leg of the DC isolator. And by the way, I should draw them as ganged. They're ganged like this. So that means I need a per switched leg voltage rating for this product. If the product is sold with a rating for both poles being operated, breaking the current across both switched legs, then it's probably going to be approximately half, but don't assume that. Check in the data sheet. So that's one of the biggest mistakes people make, is thinking that it says the product's rated for 1,000 volts on the box, but in fact it's only probably about half of that on each switched leg. And also the thing about DC isolators is their voltage rating is dependent on their current. So as the current goes down, their voltage rating goes up. So it might be 1,000 volt rated at 16 amps, but it's only 800 volt rated at 20 amps, and at 32 amps it drops down to 600 volts, etc. So you've got to get those tables from the manufacturer. A lot of the specialist wholesalers will already provide you with this data, so that's a good thing to plug away your wholesaler with, saying, oh, can I please get the data sheet for this one? It might be in the box. It might not actually be appropriate for New Zealand or Australia, so you really need to check some of those things. Okay, so that's just explaining a transformerless, and so I'll go non-isolating. So non-isolating inverter, which, by the way, is almost every inverter on the market now. You might think that we always go to safer solutions, but actually we rely more and more on electronics to protect ourselves with non-isolating inverters. Transformers inverters were inherently a little bit safer, but they're less efficient, more expensive, they were heavier, and so weren't so popular. So that's let me just jump back here. There we go. So that's a little overview of some of the things to consider when you're installing a PV array. I took you up to the DC terminals of the inverter, or the power conditioning equipment, to use the terminology in the standard. What I'd like to do is go beyond the inverter next week and cover off on the AC side of the standard, which is 4777. Part 1 is the installation standard. And it's a joint standard with Australia and New Zealand, so it's equally applicable to both countries. Now this week I've been running these daily live streams at 3 o'clock Australian Eastern Standard Time and 5 p.m. New Zealand Standard Time. Next week, I've got my kids back here. I share them with my ex, and so I'm going to have kids at home that I've got to homeschool. So I'll probably only do 2 or 3 next week. So just watch the usual social media channels for announcements of my next live streams. And I'd love to get some comments about what you want to learn more about. So, in the, what do they always say, in the comments below, put some requests about what you'd like to see more of. And I guess I better say you should really try and subscribe. That helps me build my channel, and click that bell icon if you want to know whenever I've posted a new video. Particularly if, like today, I bug it up and manage to stop it midstream and have to start it again. Okay. Well, thanks to everyone for turning up today, and hope to see you next week. Okay. See ya.